Hello all, I am Professor Chaitanya GD, Assistant Professor, Department of Mechanical Engineering, MIT Mysore. Today we are looking at Fluid Mechanics and Machinery Laboratory. The subject code is 18MEL57. Now we have to define what is fluid first. We know that a matter can exist in three states. It can be a solid or liquid or gas. Now solid is one category and liquid and gases are considered as fluids. Now how do you differentiate solid from that of fluids? It is by the behavior of the fluid or behavior of the substance when it is subjected to shear stress. Now look at the definition of fluid. Fluid is a substance which deforms continuously under the action of shear stress. That is, if you consider air or water, they are the one which are considered as fluid. That is, liquid as well as gases are considered to be fluids. Now, if you consider a solid material between two flat plates, let us say that the bottom plate is fixed, and if you are trying to move the top plate, it is the solid is subjected to shear stress. Now, if it is a solid, it tries to resist to the shear stress. So, in solids, rate of stress is proportional to strain. Whereas, if there is a fluid in between these two flat plates, let us say one is fixed plate, the other one is a movable plate. Then, if you give a certain shear stress or certain movement to this top plate, it keeps on moving. However, the fluid does not resist to the movement of the top plate. That itself is the way by which it is different from that of a solid. That is what we are trying to say, which deforms continuously under the action of shear stress. Even for the small shear stress also, it does not show any resistance, whereas in case of solids, it does exhibit the shear stress and it resists to the deformation. Now, coming on to the classification of fluid mechanics, we have fluid statics. That is, if you are studying fluids at rest, we call it as fluid statics. If you are studying fluid at motion, it can be fluid dynamics or kinematics. But in fluid dynamics, we consider the forces. In fluid kinematics, we do not consider the forces. For example, fluid statics problems are like if the forces exerted on a dam, or if you have a water tank, the forces exerted or the pressure exerted on the walls of the tank, that is the problem of fluid statics. Then fluid dynamics, we do consider the forces. For example, impact of jet, or you can also consider flow through the orifice. Then in case of fluid mechanics, we are interested in the velocity or acceleration of the fluid particles. Now, what are all the application areas of fluid mechanics? As we said, fluid is the liquids and gases. Now, wherever you come across with the problems of liquids and gases, there all we have the applications of fluid mechanics. The problem of fluid mechanics might have started from the, if you look at the history, the transportation of liquid from one place to the other place was the biggest problem, or the first fluid mechanics problem which ever have encountered. Now, look at this. Heating, ventilation and air conditioning. So obviously, as we said, here we are interested in cooling the fluid, we are interested in supplying the fluid, we are interested in exchanging the heat with the fluid. There are we come across with the fluid mechanics. Then fuel line, fuel pump, injector, even the mixing of the fuel in IC engines or automobiles, we will come across with the. That means to say, designing or analysis of these equipments need the knowledge of fluid mechanics. Now hydraulic brakes, power steerings, then aircrafts, boats, submarines, wind turbines, then transportation of water from one place to the other place, or crude oil, natural gas, and designing of such pipelines, pumps, or if you consider the refrigeration systems, the nozzle or the evaporator, all the in case of automobile you may have to have a radiator, all the components which involve the fluids, there all we need the knowledge of fluid mechanics. Now, what are the syllabus which we are going to study? Part A is individual experiments and part B is group experiment. Here we said that fluid mechanics is you are studying the behavior of fluid, and machinery laboratory we have machineries which convert fluid power to the mechanical power. So part A we are studying majorly the problems of fluid mechanics, where you may are interested in measuring the flow. Such experiments are there in part A, whereas in part B we are much interested about the power producing devices or machinery equipments which we are talking about. Now look at the part A. We have lab layout, then calibration of instruments and standards to be discussed, determination of coefficient of friction of flow in pipes, determination of minor losses in flow through pipes, application of momentum equation for determination of coefficient of impact of jets on flat and curved plates. Then we have part B, performance on hydraulic turbines. We have Venturi, Francis turbine and Kaplan turbine. Then performance of hydraulic pumps. We have single stage, multi-stage centrifugal pumps, a reciprocating pump. Then performance test on two-stage reciprocating air compressor. Then performance test on air blower. So this part is majorly machinery, whereas this part is the problem of fluid mechanics. Then we have to discuss the course outcomes. The first course outcome is apply the methods of measurements of quantities and principles of fluid mechanics to comprehend and conduct tests on fluid flow and fluid machinery and documenting the outcome of experiments. Then second CO is calculate the required parameters with the help of tabulated data from the experiments using appropriate analytical principles of fluid mechanics. Then analyze the experiment's results and effect of variable parameters on performance of fluid machinery. Now if you look at the exam pattern, we have internal marks for 20, then external is for 80 marks.
Namaste, this is Mallikarjuna, working as an assistant professor in Department of Mechanical Engineering, MIT, Mysore. Today we are in Fluid Mechanics and Machinery Laboratory. The subject code for the lab is 18MEL57 and it has credits of 2. In this session we will be conducting the experiment on Venturi meter. Venturi meter is a device which is used to measure the flow of the fluid through the given passage. The aim of the experiment is to find coefficient of discharge of given Venturi meter. Operators, that means the equipments that are supporting us to conduct the experiment, are Venturi meter experimental setup as well as the stopwatch. Let us look on to the Venturi meter sketch now. This portion is a pipeline. Here also pipeline is present, to which the Venturi meter is attached. This Venturi meter consists of 3 sections. One is the gradually decreasing cross-sectional area, which is actually called as a converging portion. Second one is the constant cross-sectional area, which is actually called as throat. And the third portion is the gradually increasing cross-section area, which is actually called as diverging portion. As soon as the flow happens through the pipeline as well as through the device, when fluid enters into the converging portion, here the pressure of the fluid starts to reduce. Along with that, velocity gains up, I mean pressure reduces, velocity rises. And in the throat portion, the velocity as well as the pressure remains constant. And in the divergent portion, the pressure starts to build up and the velocity comes down. If we clearly look onto the various parts, the converging portion is of shorter length and the diverging portion is of longer length, because here the sudden reduction in the pressure that has happened, which rises the velocity to a maximum value. In order to regain this pressure conversion in the divergent portion length has been increased. That means whatever the energy, pressure energy which has got converted into the velocity has to be again converted into pressure energy in the divergent portion. That is why the length of the divergent portion is too high in divergent portion. So this is how the Venturi meter actually works. This actually works on the principle of Bernoulli's equation. Bernoulli's equation or Bernoulli's theorem says that the energy possessed by the fluid through a passage, given passage, remains constant. If I look onto the equation, we have three different terms over here. First one is P by rho g, which is called as the pressure head, V square by 2g, which is nothing but the kinetic head, and the Z is the potential head. Whatever the energy possessed by the fluid, all those things will be in these three terms only, which these three terms remains constant at any given section of the flow device. That is what is the meaning of Bernoulli's equation. Say for example, in the convergent portion, the pressure energy has got converted into kinetic head, I mean the velocity. The same has to be reconverted into pressure energy in the divergent portion, I mean kinetic head has to be again reconverted into pressure head. That is what happens in the divergent portion, but we need to make sure that overall energy possessed by the fluid at any section of the device remains constant. That is what the Bernoulli's principle says. So this is what is regarding the working principle of Venturi meter. These flow devices are usually studied in the subject of fluid mechanics. In fluid mechanics, we will be studying various flow measuring devices such as Venturi meter, orifice, notches, rotameters, petard tubes, and their derivations. Actually, we need to derive the things for theoretical discharge, etc. It will be highly studied in the subject fluid mechanics. If we come to the application part, Venturi meters are actually used in measuring the flow through the passages, especially measuring the flow which is happening through the pipelines. If we come to the medical field, the flow of the blood can be measured, as well as the oxygen flow through the oxygen pipelines, which is used for the patients, that can also be measured with the help of the Venturi meter. Wherever we find the flow of fluid, there we can apply the Venturi meter to measure the flow of the fluid. So this is what regarding the application of Venturi meter. Okay, this is the experimental setup for the Venturi meter. If you look onto the setup, this consists of three different flow measuring devices. First one is a Venturi meter, second one is orifice meter, and the third one is nozzle meter. So we will be concentrating on the pipeline to which the Venturi meter is attached. If you look onto the various other components of the experimental setup, this is the sump in which the water is dumped or stored, and here we have a centrifugal pump in order to pump the water through the flow line. This is a rotameter which is used to measure the actual flow rate of the fluid, and these three are the pipelines with respect to the different flow measuring devices. This is the pipeline connected to the Venturi meter, pipeline connected to the orifice, and pipeline connected to the nozzle meter. And this is the flow controlling valve with which we have to control the flow, I mean the actual flow which is happening through the pipeline. These three are the differential manometers. The Venturi meter is connected to the first manometer, the orifice is connected to the second manometer, and the nozzle is connected to the third manometer. We need to make sure these valves are closed always. Before conducting the experiment, we need to be very careful. We are operating with Venturi meter. We need to make sure that the valve of that particular pipeline should be open and other valves are closed. By operating this valve, we need to adjust the required flow rate, which has to happen through the Venturi meter. Now let us start the experiment. You need to make sure before conducting the experiment the main switch is on, and then you need to switch on this button. Now the flow is happening through the device. You can see over here. Now we need to fix the actual flow rate that has to be fixed with the help of this valve. Please adjust this valve so that you will get the value around 36 over here. Okay, by operating this valve, we have set the actual discharge into 36 liters per minute. So 36 liters per minute is the discharge which is happening through the device now. We now to look on to the pressure difference, pressure variation which is happening at various sections of the Venturi meter. We need to open these two valves. Now we can observe there is a variation in the columns of the mercury manometer. This is the reference level. One of the columns is going up from the reference level and one of the columns is going down from the reference level. From the reference level, this height is actually 3.5 centimeter, which is above the reference level. Because of that, it is taken as positive, and another reading is 3.5 below the reference level. Because of that, we have taken it as a negative while calculating. So this is what is regarding the first experiment. Only three things needs to be observed. Initially, we need to set the flow with the help of this valve to 36 liters per minute, and by opening these two valves, we need to look on the pressure difference in the form of height of mercury. Okay, let us go through the second trial now. Again, by operating this valve, we need to adjust the actual flow rate. For the second trial, we have fixed the value of around 40 liters per minute. So by operating this valve, the value, the actual discharge has been fixed to 40 liters per minute. That means the 40 liters per minute of water is flowing through the pipeline. Again, we need to look on the pressure difference at various sections of the Venturi meter. Now, the pressure difference we need to look on. One of the reading is reading the value of 4.7, that is nothing but the positive reading. That means it is above the reference point, and another reading is around 4.8. This is below the reference point. That is why it is taken as negative. So this difference is considered as the pressure difference in the form of height of mercury limit. So these are the key values which we need to look onto while conducting the experiment. Very first thing is actual discharge and the pressure difference in the mercury column. In this section, we will be looking onto the tabular column. We have conducted two trials. In the first trial, let us look onto the terminologies now. H1, H2, where H1 is the limb height of the manometer on one side, H2 is the limb height on the manometer on the second side. Difference in manometer height, that is H1 and H2. This difference has been taken over here in terms of meters. Here it has been mentioned in terms of centimeters. Here it has been mentioned in terms of meters. And this height, which is measured in terms of manometer fluid, which is nothing but the mercury, has been converted into height in terms of water. So that is what is there in this column. And actual discharge, which is happening through the device, that is nothing but Venturi meter, has been measured in terms of liters per minute with the help of another measuring device, which is nothing but rotameter. This actual discharge, which is in LPM, has been converted into meter cube per second. This is also the actual discharge, but the units are different over here. And with the help of the derived formula, we will be calculating the maximum flow that can happen through the device, which is nothing but the Q theoretical in terms of meter cube per second. And finally, the aim of the experiment, which is nothing but coefficient of discharge, which is nothing but ratio of Q actual divided by Q theoretical, or actual discharge divided by theoretical discharge, that has to be calculated with the help of CV formula. That is what is there in the final column. If I look onto the first trial, initially the actual discharge which has to happen through the device has been fixed, that is 36 liters per minute. For this actual discharge, we have measured the mercury column length. One of the column is reading the value of 3.5 centimeter, and another is also reading 3.5, but we have introduced a negative sign over here because one of the column is going up from the reference point and another column is going down from the reference point. Which is going up as considered as the positive, which is going down as considered as a negative. And if we take the difference of these two, we will get the value of 7. If we convert this centimeter value into meter, which will be 0.07. If we convert this value, which is in terms of mercury height, into the water height, that comes around 0.882. Actual discharge, what we have measured through the rotameter is this much, and if we convert this LPM into meter cube per second, that becomes this much, and Q theoretical with the help of the available formula that has taken the value of this. If we look on to coefficient of discharge, which is nothing but Q actual by Q theoretical, which will come around 0.97. Let us look on to the calculation part now. These are the observations what we have to do while conducting the experiments. We have 3 different sections in the Venturi meter. Here, A1 is the initial area of the Venturi meter in terms of meter square. That means the area as soon as the Venturi meter device is taken into consideration. This is the area at the initial portion of converging section. That is what is initial area of the Venturi meter, which is notated as A1. A2 is the throat area of the Venturi meter. Throat is the second portion of the Venturi meter. That area is notated as A2. H, capital H, that we have seen over here, which is nothing but the pressure difference which has been measured in terms of mercury has been converted into water pressure difference. So that is what is measured as H in terms of meter. Q, actual discharge, that we have actually fixed in terms of LPM, and it is measured with the help of rotameter. Q actual, the same value has been converted into meter cube per second from LPM. Q theoretical, the maximum flow rate that can happen through the Venturi meter in terms of meter cube per second. And CV is nothing but Q actual divided by Q theoretical, which is nothing but the coefficient of discharge of the given Venturi meter. Let us go through the trial number 1 calculation now. Very first thing is capital H. As we have already seen, capital H is nothing but head in terms of meters of water. We have the formula for that. Capital H is equal to small h. This small h is nothing but head, which is measured in terms of mercury, which is nothing but the manometer liquid. Sm, specific gravity of the manometer liquid, which is nothing but mercury, divided by specific gravity of water minus 1. Here the small h has been measured in terms of 0.07 as a meters of mercury, that has been substituted over here. That means 0.07 is in terms of meters of mercury, 13.6 is the specific gravity of the mercury, 1 is the specific gravity of water minus 1. So this is going to yield us the value in terms of meters of water, because I have substituted pressure difference in terms of mercury in meters. So because of that, the answer is also in terms of meters of water. The value is 0.882, that has been written over here. The second thing is theoretical discharge. We have derived theoretical discharge equation in the theory session. The equation comes like this: A1, initial area of the Venturi meter; A2, throat area of the Venturi meter, square root of 2 G gravitational force into H. Please look on to this H. This H is the capital H. Capital H is nothing but head in terms of meters of water, not in terms of meters of mercury. Capital H divided by square root of A1 square, initial area of the Venturi meter square, minus throughout area of the Venturi meter square. For the trial number 1, if we substitute the corresponding values, we will get the theoretical discharge as 5.148 into 10 to the power of minus 4 meter cube per second. That is what I have written in this column. Next thing is actual discharge. As I have already mentioned, actual discharge which has to happen through the device has been fixed and it has been measured with the help of the rotameter, and the fixed value was actually 36 liters per minute. This has to be converted into meter cube per second. For that purpose, we have a formula over here. Little bit of conversion. Q actual is nothing but the Q which we have fixed or which we have measured with the help of the rotameter, which is in terms of liters per minute. In order to convert that into meter cube, I have divided that by 1000, and now to convert the minute per minute into per second, I have divided the value by 60. Rotameter value divided by 1000 into 60 will give me the value in terms of meter cube per second. For the first trial, the Q, small q is 36, the value measured by the rotameter. I have substituted that over here. Divided by 1000 into 60 will give me the value of 0.005 meter cube per second. That is what I have mentioned in Q actual. So now Q theoretical is known to us as well as Q actual is known to us. Now finally we have the formula for discharge coefficient or coefficient of discharge. Coefficient of discharge, which is nothing but CD, is equal to Q actual divided by Q theoretical. For the trial number 1, Q actual is nothing but 0.005 and Q theoretical is nothing but 5.148 into 10 to the power of minus 4. If we divide Q actual by Q theoretical, we will get the coefficient of discharge for the given flow measuring device, which is nothing but Venturi meter. For the first trial, it comes around 0.97. Similarly, if we repeat the experiment for the second trial, if you want to repeat the experiment, only thing that we need to change is the actual flow rate. The actual flow rate has been fixed to 40. For this 40 value, we have head in terms of waters. Head comes around this much. Q actual is actually 40, that has been fixed by us. If we convert that into meter cube per second, the value will be around 0.0052. With the help of the formula, if we measured the Q theoretical, it will come around 5.3 into 10 to the power of minus 4. If you want CD, we need to divide Q theoretical by Q actual. So Q actual by Q theoretical will be around 0.98. So by looking onto multiple trials, the value of CD is around 0.97 to 0.98. So this is what is the value range for, CD range for the Venturi meter. After doing the multiple trials and looking onto the values of CD, if we take the average of CD value, it will come around 0.98. Even theoretically, while we speaking, the range for the CD is around 0.95 to 0.99. So that the found value is in the acceptance range. So this is what was our aim. Our aim was to find the coefficient of discharge for the Venturi meter that has been found around 0.98, even it is matching with the theoretical range. So this is what is regarding the experiment. So now let us look on to the probable Viva questions that may be asked in the experiment. Very first one is,
state Bernoulli's theorem.
Bernoulli's theorem says that energy possessed by the fluid in any given section remains constant. If I look onto the equation consists of three different terms. First one is the pressure head, P by voce. Second one is V square by 2G, which is nothing but kinetic head. Z is the potential head. All these three things upon addition remains constant at any section of the given flow measuring device. Second question is,
name various flow measuring devices.
Various flow measuring devices are Venturi meter, orifice, pitot tube, rotameter, notches, etc.
In which section of the Venturi meter pressure intensity will be maximum and minimum?
We have seen the working principle of Venturi meter, wherein the pressure with which the fluid enters into the inlet portion, converging portion, is maximum. At the inlet portion, the pressure intensity is maximum, and it reduces to the minimum at the throat position. So, maximum at the inlet portion and minimum at the throat position. Next question.
Why divergent cone is longer than convergent cone in Venturi meter?
Yeah, if you look onto the converging portion, the pressure energy has been converted into velocity. Sudden variation in the pressure is there. So this pressure energy has converted into velocity over here. Again, this velocity needs to be converted into pressure. So in order to convert the converted velocity into the pressure, the divergent portion has been provided for a longer distance. That means whatever the pressure loss which has happened over here, that has to be regained. In order to regain the pressure, again the divergent portion has been provided with the longer length.